Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Pleasure to introduce Eli Berger. He got his PhD from the Technion here. Princeton, and he is now he is now a postdoc at the Institute of Advanced Study. He will tell us about Menger's theorem for infinite graphs.
Okay, so this is a joint work with Ron Aharoni, and well, what we do is we have a graph. You can think of it as some network. And you have two special sets in it, say A and B. And you can think of A as places where some information is obtained. And you can think of B as some places where you need this information. And what you need is as many paths from A to B. You need to transmit this information, and this path should be disjoint because you don't want any traffic jam. So, well, there is some trivial upper bound for this. This is the bottleneck, which is the minimal set separating A from B. So if you remove this set from the graph, you will no longer have any path from A to B. Now, it's quite easy to see that this is really an upper bound for the, you can't achieve more than the bottleneck. But Menger proved that in 1927, actually, there's an inequality. You can always actually achieve this bottleneck. So this is a classic theorem. You usually see it in a first course on graph theory or algorithm theory. What's a little bit harder is the infinite case, which is what I will speak about today. And well, the question is the same. You have a graph, you have two sets A and B, you have a set of paths from A to B, possibly an infinite set. And the question is it still true that the cardinality of the minimal separating set is equal to the cardinality of the maximal number of paths? And this turns out to be true. It was proved by some young mathematician. You can see here is how young he is. Well, at this year he was young. Paul Erdos. And the idea was very simple. Just take the union of a maximal family of paths. Take all vertices along each of these paths. And the idea is that if you have an infinite set, then you can multiply it by every finite number, or even by Aleph 0, it will still be the same. So the cardinality of the number of x's here is equal to the cardinality of the number of green paths here. But of course, this is not what we thought of. I mean, this is not what we have in the finite case. In the finite case, we had something very strict. We had, on every path, we had exactly one x. So the question is, can you do it without cheating? You actually want exactly one x on every path here. And this is the Erdős-Menger conjecture. There exists a family of disjoint paths, and the set of vertices from each one of them, so that the set separates A from B.
What is the earliest written reference you have found?
In 1967, I think. It was in a book of Nash Williams. So I will speak today about this conjecture. And I will start from some ideas in the finite case. Well, in the finite case, if you want an algorithm to find, say, the minimal separating set or the maximal number of paths, one way to do it is to it's enough actually to do it in the bipartite case. So in the bipartite case, where we have two sets, A and B, and say every edge is directed from down upwards, and what you need is a set of disjoint paths. What is a path? A path here is just an edge. So you need a set of disjoint edges. That's called a matching. And you need a separating set. What's a separating set? A set of vertices catching all the edges. And you need it to be, and this is what it says. You have a matching and a set of one vertex from each of them so that this set is separated. And this is, I will show that it's enough to prove this. I mean, suppose you know how to find, you have an algorithm to find a Koenig structure. I'll show you an algorithm to find a Menger structure. This is, take your graph. Now multiply all the vertices. And add all these little edges from the two copies of each of the vertices. So what we have now is a bipartite graph. In a bipartite graph, you can apply Koenig's theorem, and you get some Koenig structure in the bipartite graph. Plus, we add all of these, we also note them by x's, just for convenience. And now if you take this and you go back to the original graph, what you get is a Menger structure. Let me just show you that these x's are really a separating set. Well, just take any path here. Let's say this path in the original graph. And let's go back to see how it looked here. Then, how many x's do you have here? You have two artificial x's here.
Excuse me, what is the role of the arrows?
Arrows, these are the arrows from the, these are the arrows, originally we had a directed graph. So we had arrows, we had the directions.
So somehow in the new vertices, the arrows are reversed?
Yes, they are reversed because we want it to be a bipartite graph, and we want
so you split every vertex into ingoing and outgoing edges, and then put a reverse arrow there.
So suppose we have this path.
Yes. It's not an oriented path now.
This is it's when you contract these edges, it becomes an oriented path. So if you have, we have an edge, we have the path here with say 2 edges, then on each of these edges we add at least 1 x. And plus we had 2 artificial x's. So we had, originally we had k edges, now we had k plus 2 edges. And we have k plus 1 vertices here, 3 in this example. So by pigeonhole principle, at least one of them has 2 x's. So in the original graph, this path meets our separating set. So this is indeed a separating set. Okay, now, Koenig's theorem is very closely related to another classic theorem, which is Hall's theorem, saying that if you have a bipartite graph, you can always find some of 2 constructions, either a marriage or an obstruction. Obstruction is well, several points here that not together less than the numbers. So there's no edge from here outside. And this is if you know, if you have an algorithm to find a marriage over an obstruction, then it's very easy to find a Koenig structure. Just, or as long as you have an obstruction, find one and find a minimal one. A minimal one must look like this. So you must be able to find a matching of everything except for one. And if you do it again and again, eventually you have. So for this matching, take these to the separating set. And for a marriage, take these to the separating set. And eventually, you have a Koenig structure. Now, how do we say find a matching? Well, this is just if you have this easy lemma that if you have something with no obstruction, and you have any vertex from A, then you can match it to some vertex in B, and when you remove A and B, when you remove this vertex small a and this small b here, then you will still have no obstruction. So you can do it again and again and again, and you will eventually you have a matching of all of A to B. Now, algorithmically, this is not what we usually do, because although this lemma is true, I don't know any algorithm that gives you this B. So algorithmically, what we do is we have this A, we match it to something in B, but we don't care if it's not this B in this lemma. Then we continue until sometimes we can't do it, and then we go through some alternating path. So we do reserve the right to change our mind in the future. And you will see that also in the infinite case, alternative paths play a very essential role. Now, let's show some history of this thing. In 1974, Prodevsky and Stephens, for the bipartite case, they proved something like Hall theorem. Well, Hall theorem itself is not true for the infinite case, but there's something like Hall theorem it's true, and they use it, and they prove Koenig theorem with it for countable graphs. And in 1922, Nash-Williams and Aharoni and Shelach proved generalized this result for any cardinality of bipartite graph, and Aharoni used it to show that actually Koenig theorem is also true for any cardinality of bipartite graph. Now, okay, so since 1993, Koenig theorem for infinite bipartite graph is known. And we have some reduction of Menneker theorem to Koenig theorem. So what's the problem? Why doesn't the reduction from Menneker theorem to Koenig theorem work in the infinite case? Any idea what might be the problem? So the problem is that we don't really get exactly what we want. We do get paths. And all these paths, if they start at all, they start in A. If they end at all, they end in B. But nobody guarantees that they will start at all or end at all. You can find some paths that don't start anywhere, and you can paths that don't start and never end, and you can find some paths never starting and never ending. And the question, how do we avoid this? And the way to avoid these infinite paths is not to use Koenig theorem as a black box, but to actually go to the proof of Koenig theorem and step by step being careful not to make an infinite path. And this is very problematic. One reason why it is problematic is that, as I said, Hall theorem is not. I mean, we have Hall theorem, some Hall type theorem in infinite graphs, but Hall theorem is only in bipartite graphs. And the question is, what is the counterpart of Hall theorem when you don't speak about paths, you don't speak about edges, you speak about paths. So what is Hall theorem? Hall theorem says that if you have one of two things. You either have a marriage or you have an obstruction. So the counterpart of a marriage is quite easy to see what it is. It is a linkage. What is a linkage? You have a set of disjoint paths from all of A to some subset of B, not necessarily all of B. This is the counterpart of having a linkage, of having a marriage in a bipartite graph. The counterpart of an obstruction is a little bit more complicated. What you use is a notion of a wave, and this is more or less half of what we want in Kane theorem. So, in Menger's theorem. So, what do we want? We want a set of paths from A to B, and someplace on them a separating set. What a wave is just half of this, only from the bottom up, but it stops somewhere in midair. And the only thing we want is that the place where it stops is a separating set. Now, a wave might use all of A, and then we say that this is a full wave. And there might be some vertices of A which are not used. And these vertices will be called, and in that, if there is some vertex not used, then we call it a hindrance. Why a hindrance and not an obstruction? Because now it's not an if and only if condition. It might be the case that there are hindrances and nevertheless there is a linkage. But the theorem, which is actually equivalent to the conjecture, to the Erdős-Menger conjecture, is that if a wave is unhindered, then it is linkable. So let me just show this equivalence. So we have this conjecture of Aharoni, and we have the Erdős-Menger conjecture. So let me start with showing that what's the easiest part? That Erdős-Menger implies Aharoni. Well, suppose we know Erdős-Menger conjecture and we take some Menger structure in the graph. Now, two things can happen. One possibility is that it uses all of A. If it uses all of A, then we're OK. This is actually a linkage. If it doesn't use all of A, so it doesn't use this, then we can just take the lower part, and we have a hindrance. So this direction is pure.
What's a hindrance again?
A hindrance is a wave not using all the vertices of A. So in the final case, hindrance is really an obstruction for having a link, because here you have more. Here you have more vertices than here. So you can't get from here to B because you can't have such many paths. Now the other direction is a little bit more complicated, but so you take a wave. So we have A and B, and you take a wave, and you'll have to believe me that there is some wave which is maximal. So, well, this is maximal, meaning that you can't continue it and still having a wave. So now look at this graph from here to here. Does it have a wave? Well, it has a wave. It has this wave. A wave can contain paths of length 0. But it doesn't have any other wave. And since this is a full wave, there is no hindrance. So in this graph, there's no hindrance, so there is, by Aharoni's conjecture, a linkage from here to here. And this is the Menger structure. So from now on, what we need to prove is that some unhindered, is this conjecture, that in an unhindered graph, there's always a linkage. And the main lemma to prove this is something similar to what I showed you in the whole theorem, that you have sets vertices in A. You need to somehow make a path from A to B. So if you remove the path, there's still no hindrance. And at least in the countable case, it's easy to see why this immediately show that this graph is linkable, because you can just order the vertices and one by one link them to B, and after omega step, you have a linkage. What I will show you is actually something stronger than that. I will show you that suppose you just had some oracle. That if we give this oracle some finite set, it tells us if after removing this set, we have a hindrance. Then we can find this path in a finite time. So let's see this. Before we see this. This was proved in 1987, so this proves the Erdős-Menger conjecture for countable graphs. It's due to Aharoni. And in 1997, Aharoni actually proved that it's enough to prove this lemma. It's enough to prove this lemma to show that the Erdős-Menger conjecture is true for the directed graph of size Aleph1. And actually, he said it might be the same thing, that the same thing works for Aleph2 or any cardinality. He didn't show it. And it turns out to be half true. I mean, it doesn't require any more new ideas, but it requires much, much more work to show that this is true for more graphs. So now I will show you this lemma. So we have a vertex in A. We have a graph which is unhindered. We want to find a path from A to B, and we remove it and still be unhindered. So let's just choose a path and go along this path. So at the beginning, the graph is still unhindered until at some point it becomes hindered.
By the picture, you mean you delete the?
Yes, I started deleting A. First I deleted this, then I deleted this, then I deleted this. So far it was unhindered, and then I deleted this.
Endpoint you put into A.
And no, I just deletion.
Just deletion. Okay.
I mean, okay, we will see later that there are something more complicated than deletion, where you put things in A. But so far it's not. You just delete this, delete this, delete this, and then when you delete this, you have a hindrance. So what do we have? We have here a graph with no hindrance, and after we delete this, we have a graph with a hindrance. And we have a lemma using some idea of alternating path. And if you have a graph, you remove one vertex, and suddenly you have a hindrance. Then in your original graph, you had some wave reaching this vertex. Why is this? Because suppose here you have a hindrance. Try to find alternating path getting from hindered vertices, from vertices not used. And put everywhere the maximal place where you can reach with such alternative path. Then somewhere you will be able to reach to x. Otherwise, when you add this, when you add it, it's still a hindrance. And now you can go along these alternating paths, and you actually get a wave using this. So I won't show you that it is a wave, but it's not very hard to see that. So we have enhanced the graph. We delete the vertex, so we have in the graph. So in the original graph, in the graph before the deletion, you have a wave reaching this vertex. And well, now we continue. We choose some other path. We go along this path until it's hindered, and then we go another way. And we continue this way again and again and again until eventually all paths are exhausted and we have some. So if at some point we reach B, then we are happy. We remove this path. We remove the, and we know that removing it keeps the graph unhindered. If not, then eventually all the paths are exhausted, and we have some countable tree here. What do we do then? Let's look at this red set of paths. Well, it is a wave. A wave where? A wave in the graph when we delete the tree. But it is more than that. For each vertex in the tree, and for each edge coming out of it, we know that at some point we tried to add this vertex, and we did. If we didn't add it to the tree, we added it to the wave. So these waves go through all the vertices from which you could escape from this tree.
Excuse me, the red is a wave or a union of waves?
Okay. Every time, so we had, we took a wave, and then at the next time, we started the wave from where the first wave ends. So we have this is some way to compose two waves. We have a wave ending here, and suppose we have some other wave. Then we ignore whatever this red wave does under the place where this green wave ends. We only look at what it does above this. And now we have some third wave looking like this. So this third wave is a continuation of the green wave along the red wave. So
it uses green unless it can't, and then it uses red if it can?
Yes. So what we always continue, we only go forward. We don't change our mind. If we went through this, we will not we will not change this path. Only continue from here. And this is why we are allowed to take the limit. So.
But when you add the next time, you had a vertex that you wanted to reach there. Why wouldn't the composed wave be one that actually reaches there? Why wouldn't it be?
If we already reach, if this was already in the red part, then we actually don't even need to consider going this way.
Okay.
So we only consider edges going to the part which is not red. In fact, we only need to consider going to vertex from which you could go all the way to B, not going through a red vertex.
Okay, but the way you get to this new vertex with the green might cross some of the red paths.
The way we
This strand, which is third.
If you have, you say if we have something like this.
This strand, that is the third from the right, which reached the new vertex.
What?
Third from the right.
Third from there. This?
Yeah, that one that reached the new vertex.
Yes.
Say it went through one of the old strands.
If this went through, okay, if such a thing happens, okay, one of two things. Either you can't reach from here to B, or you will see that one of the this can only happen okay, look, if you can reach from here to B, then so going this way and then going to B is some path from A to B. Okay, so it must meet this the original, the way that was before. It must meet some place where this original wave ends. So it must say it meets this point, then this wave is continued. Okay, so it is sub. There are many subtleties that I ignore here, because only have the 1 hour, but there are many subtleties here. I mean, but it works. Okay, so eventually all the paths are exhausted. So this red wave is a wave in the original graph minus the tree. But it also goes through every vertex from which you could escape from the tree. So it actually is a wave also in the original graph. Because every path, even if it meets the tree, then the last time when it tries to get out of the tree, it must meet this red wave. So it is a wave in the original graph. And it does use small a, so it is actually a hindrance in the original graph. And this is a contradiction because we assume that the original graph was unhindered. So now, a question is, what do we do when the graph is not countable? Well, when the graph is not countable, then first of all, we can. First of all, the thing to do is to use a Transfinite algorithm. So, what Transfinite algorithm? Well, it's the same thing as an algorithm, but make a step, another step, then make the omega steps, and then omega plus 1, omega 2, and we can continue this way, actually indefinitely, transdefinitely. So we have this idea of Transfinite algorithm. You can continue the tree beyond the omega step. But the problem is that when we take the limit, of many hindered graphs, the graph we obtained is not necessarily hindered. It might get hindered. So we can't reserve, like in the final case, we can't reserve the fact that our graph is unhindered. What we can reserve is some much weaker property, and this is that there is no hindrance after removing a finite subset of the tree that we construct. So this solves the problem. It makes many, many new problems. I just try to give you the taste of what new problem it costs. So suppose we are done. Okay? We made this algorithm. We have this tree. Every finite subset of the tree that make a hindrance. And every way you could escape from the tree, it will make a hindrance if you remove it. So let's look at one vertex from which you could escape from the tree. This blue vertex. And what do we know? We know that why didn't we add it to the tree? Because there is some finite subset of the tree, so that the blue together with the green, if you remove the blue and the green, you get a hindrance. But we know that if you remove only the green, there is no hindrance. So in the graph where you remove the green, there is a wave meeting the blue. But the problem is that this wave might go through some vertices in the tree that are not in this green set. So let's say it explicitly. Let's take all the vertices from which you could escape from the tree. Let's call it big Y. So for every small y in the set, there exists some finite set. So if we remove these sets, this set and A, then we have some wave reaching Y. But it's not a single set. For different y's, we get different things. And well, the solution to this now stand in some idea that actually we had before. And this is similar to what Latsi said before, but, about adding this vertex to A. So we had two ways to remove a vertex. One is to just remove it and forget about it. And you have a new graph without this vertex. The other idea is you just remove all the edges coming to this vertex, and you add this vertex to A. So this is called taking a quotient over the vertex. And we had many debates, what is better, taking a quotient or deleting? And well, a quotient has a very good advantage that if you have a quotient over some sets, and a quotient over, if you have a wave in a quotient over some set, and a wave in a quotient over another set, then you can combine them to some wave in the quotient over both of them. So we have a big debate on what should we take, this kind of removing or that kind of removing. And eventually, it turned out that we need them both. So we have some argument that at some points removes vertices, and then to show that it really works, it uses quotients. So what we do is this. Well, for some vertices, we call them blockable. We can take a countable quotient, and with this quotient, we can take some wave separating this vertex from B. And now in the tree, we look at all the unblockable elements of T. So it might be an uncountable case, I don't know. And now,
So what is a countable quotient exactly?
a quotient over some countable set. So we have take a countable set, trim all the edges coming there, and add all these vertices to A.
Okay.
And now it turns out that this S has the same property as these Fs that we have here. But the advantage is that it's the same S. This S doesn't depend on small y. There is no small y. S doesn't depend on this small y. So it's enough. If we prove this lemma, then we're done. Why? Because take this G minus S minus A and take a maximal wave. So if for every vertex there is a wave reaching there, then the maximum wave, which is all of y. So this wave that reaches all of y actually is a wave in the original graph. Why? From the same idea. If you have any path from A to B, even if it goes through S, it still must go through y at some point. And since this wave reaches all of y, then this path actually meets a wave. So if we prove this lemma, then we're done. Now I will give you some taste of why this lemma is true. So we have this y from big Y. We choose in some way, I will not describe, some countable set. And we take quotient over this countable set. And we take some maximal wave in this quotient. And this maximal wave reaches y. Now, what's the problem with this wave? The problem is that it doesn't start in A. It starts somewhere in there. So what we need to do is to somehow rewire this wave so that it will reach A. It will start at A. So what do we do? First of all, some of the vertices, some of the paths here, end up in S. So we are going to remove S anyway, so we don't need to worry about these paths. The other ones, we'll need to somehow rewire them to reach A. And I will not show you how this is done, but once we make this rewiring, well, we have all the same ending vertices. So it's still a separating set together with S. And so this is indeed a wave in G minus S, in the graph when we remove S. So what else? How much time do I have? 10 minutes, okay. So this is the idea of how we prove this lemma. Now I will show you how you use. Meaning we had this. Okay, we had this lemma, and we say that in the countable case, it's easy to see why this implies that there is a linkage. I will show you why in the uncountable case it is true. So in the uncountable case, we use the idea of a stationary set. So we have, say, think of Aleph1. I'm not too familiar, you can think of Aleph1 or some other sets. And they have some, this is a set of limit ordinals there. And a set is closed if for every set there we have the limit. It's unbounded if the limit of everything is Aleph1 itself. And a set is stationary if it meets every such closed unbounded set. So what we do is we just take quotient of something. We just choose a vertex, take a quotient of it. And then we take a maximal wave, which is possibly a hindrance. And then now we take a quotient about some other vertex, and we take a maximal wave. And we continue this way. And one of two things can happen. One thing that can happen is that in many places, in a stationary set of the places of this construction, we have a hindrance. If such a thing happens, then...
So you do this for Aleph-1 steps?
Yes, Aleph-1 steps, yes. If in a stationary set of the places here, we had a hindrance, then you can actually see that in the original graph you had a hindrance. So this is one thing. If for the places where you had a hindrance is not a stationary set, then you have a closed unbounded set where you had no hindrance. So just look at where we stopped at each one of the points of this closed unbounded set. And now it's the time to use the lemma. So we number the vertices in A, say let we take A0, and then we use the lemma to find a path from A0 to B. And removing this path doesn't cause any hindrance. Now, if after removing this path we have no hindrance, and also in the path here, in this graph, we still have no hindrance. And this graph is actually, in a way, easier than the original graph because we have paths from here to here for almost all of A. So we can, it's an easier path, so we can apply some kind of induction and say that there is a linkage from here to here. So it's not. I need to show you why this really works, but you do see that this we reduced to some easier path, some countable path. And now we take a new vertex, next vertex A1, and we use the lemma to continue it to B. We on this subgraph, which is unhindered because we know that everywhere we stopped is unhindered. So we link it to B, and again we use this countability-like argument to say that we can continue it. And we do it again and again, and still we have a linkage of all of A to B. And now still, I am cheating you a bit because this, where you might end up with infinite paths, but there is a way to avoid it just by assuming that these places in a closed unbounded set behave nice. So this proves the lemma in the. This is the idea of proving the lemma in the uncountable case. I think that's it.
Any questions? What is the situation with sort of other combinatorial type min-max theorems? I don't know, Dilworth or Tat or
Tat is no. Tat is Tat. Necessary and sufficient condition for Tat theorem. I think it was proved by Aharoni somewhere in the 80s. Now it's kind of similar to here. For Aleph-1 there is some. He actually made two papers. One with Aleph-1, which is 3 pages, and one more than Aleph-1, which is 30 pages. So you have to work a lot more. Dilworth. I think
it may follow.
I will tell you what. Okay, we will show you. But it all fuzz up to the problem of finding a strongly maximal set. So for a strongly maximal set, you have a hypergraph. You have a set of sets, and you want a matching, a set of disjoint sets here, so that it will be maximal in the sense that you can say take out 2 of them and add 3 instead, and still keep it. So the Erdős-Menger theorem is actually equivalent to saying that in the set of paths from A to B, there exists a strongly maximal set. And
I mean, not 2 or 3, but any finite number, I guess.
yes, no, any finite numbers, yes. And it is, I think Dilworth is also something of that type. If you prove something like this, then it's equivalent to some. So the question is for what hypergraphs there is strongly maximal.